Hi, today we are going to learn the contagious diseases by using stellar models. Let's look at the problem. Many diseases are contagious. Some of them are vital, like AIDS and the SARS. This happened in 2003. And the most are not vital, such as the colds, smallpox, and the measles. So there's some disease when a person contracted and recovered, and he or she become immune forever, such as smallpox. For other diseases like flu or colds, a person becomes resistant to reinfection for a certain period of time, but many eventually lose immunity, become reinfected. So when we model and simulate those diseases, different diseases will make different models, depends on those facts, such as vital or non-vital, and people lose immunity or they never lose immunity. So the goal for today is first look at the baseline model. We call it SIR model. I'm going to explain what it means SIR in a minute. And then we spent some time to look at the application of the basic model and modify the model into an application to the SARS, a particular flu. And we have all those 7 objectives. We analyze the problem, formulate the problem, and look at the relationship in the conceptual level, and then build the mathematics model, which are differential equations. And then we use the stellar to solve it numerically, and finally we evaluate the model and refine the model and analyze again. So let's look at the basic SIR model. What the S stands for susceptible. Basically, we divide the population into 3 categories. And S for susceptible, I for the infected, those people who have the disease and the disease are contagious. R stands for the recovered people. We assume those who have contracted the disease and recovered will become immune to the disease forever. So in the conceptual level, the flow chart is like that. Susceptible will flow into infected when they are contagious to the disease. And the infected will eventually recover from the disease. So look at the assumptions for that particular disease. We assume there's no death because the disease is so weak, like a common cold. And second, those who recover will be permanent immune to the disease. And third, the population is pretty much located in an isolated community. There's no input and output people or immigrants. And as the basic model, we have this relationship like here. Then you have 3 stocks. If you remember how we use the stellar to model the problem. Well, we have 3 variables. S stands for susceptible, I infected, susceptible, and write it wrong. I for infected, and R for recovered. So those all change over time. So I would write this as a function of time t. And from calculus, we learned the derivative over t is defined as the limit when the dt go to 0 of the change, the population. Right now, subtract the population a moment ago and divide by the population. So that's the formal definition of derivative. But in the stellar or any numerical model, we are going to change the differential into a difference model. So differential will be approximated by difference model. So in the approximation, we simply take the limit away and make this dt small. How small is small enough? That all depends on your empirical solution. Typically, for the disease spread model, we're going to make the dt equal 1 day. That's easier to observe. So when we talk about the change rate, we're talking about a daily change rate. So in this case, the derivative is approximated as the population for today for that particular susceptible group minus the population 1 day ago. That's how you approximate that derivative. We do the same to the other 2 groups. We just look at the daily change rate. That's on one side, the left side of the equations. On the right side, just to keep this conceptual model in mind, the easiest thing is to look at this one first. Then we are going to look at that one second, then we look at this one third. So let's look at the flow in to the recovered. So let's assume the health board reports the infection take 10 days to run the course. That means in every day, 1/10 of the infected people on average are recovered. And then the daily change rate equal the population, which is I here, multiply the daily recovery rate. So every day, this many population become recovered. Now look at an example. Let's say we have 2,000 people infected the disease. Every day, 1/10 recovered. Then we know in each day, 200 people become recovered. So the change rate of recovered people is going to be approximate by the multiplication of the R, which is the daily recovery rate, times the I, which is the infected population. So in my example, if I have 2,000 people, and then this daily change rate is going to be 200. That's the easy part. So we take care of this. The R dt in here equals R times I. This R is the recovery rate. Now let's talk about the flow out from the susceptible. How many from the susceptible flow into the infected in the second part?